Now it is. But we better double check the recorder is still on. Yes, it is. All right, cool. Thank you. All right, so we'll go ahead and get started with file input output. And what I'll do is I'm going to write a program to convert the cases from uppercase to lowercase and then lowercase to uppercase. Okay, so I'll write a program in C first. Okay, make sure it works, and then I'll convert it into assembly language. By doing so, we are going to review how to flatten the program, how to do file input, and how to do file output. And all of those things are, somewhat related, to your homework assignment, and also ultimately what you're supposed to learn in this class. All right, so let's go ahead. I'll just, call that, change case, which is, what the program is supposed to do. So it would just change uppercase to lowercase, lowercase to uppercase, but everything else like punctuation, spaces, digits, and stuff like that, it will just leave it alone. Okay. I'll just call it CC, for change case, and we'll make it a, just a regular C program. Pound include unistd.h, which is what you need to do for read and write the function calls. And I don't even bother with a subroutine. We'll do everything in main. So the way we do this is we scan or we read one character at a time, and then we process one character at a time. This is going to be a loop. We will require 1 byte of storage to store the byte that we have just read, so we can decide what to do with it. So I just call this ch. I'm going to have a 32-bit integer to store the result of read and write, just so that I can make this program kind of more structured than I will make it kind of structured as any C program should be. And then we have a return 0 at the end, and now we can put in the actual code in the inside. The actual code, if I do it in C, it has to be a do while. There are several ways to do it. If you want to do a while loop, you can do it. It's just that you have to do an assignment inside a condition. So let's go ahead and do that. So we can say while, and then result equals to read. Now read is basically the same thing as system surface number 3. It's the same thing as putting a 3 into EAX when we perform the software interrupt. The first parameter goes into EBX, and that specifies which file are we reading in. But in this case, it's not the name of a file. It is the file descriptor. And file descriptor 0 always maps to standard in, okay, which is your cin in C++ or standard in regular C. So I specify a 0 here, which should go into EBX in the assembly version. The second parameter goes into ECX. That is the address of where I'm going to store the byte or bytes that I'm reading in. And then the last parameter specifies the number of bytes that I'm requesting. Okay. Now I don't usually get all the bytes that I'm requesting, but I can request up to X many bytes. But the call may come back and say, well, you requested 16 bytes, but I was only able to read 5. Okay, so we return a value of 5, which is stored in EAX in assembly. So the third parameter goes into EDX in the assembly version, but since this is written in C, it's just the third parameter. All right, and I want to compare whether it returns a 0 or not, because if it returns a 1, it means I have just read a byte. And if it returns a 0, that means I could not even read a byte, which usually means it is the end of file, so I'm done processing the input. So now we have the rest of the file here. Before we use any type of really special logic, I'm going to write this program in phases. So the first phase is really just to do echoing. Okay, you give it whatever you want, in standard in, it'll just echo it back to standard out, and I just want to see if the program can terminate in the right condition at the right time. Okay, so we'll go ahead and say, let's write that 1 single byte back out to file descriptor 1, which is your standard out, and the 1 goes to EBX in assembly. We are going to write from the same location, which is the address of CH. That needs to go into ECX, and we're trying to write 1 byte, which goes into EDX. That's my entire program, for the time being. So G++ or just GCC would be fine because it's a regular C program. -o cc cc.c. That's a lot of C's. So now we run the program CC, and we can give it a string like this is a test, and it echoes it back right away. If I type Control D on the keyboard on the blank line, it is the same thing as end of file. So what that does is it will mark the end of file, and then the attempt to read 1 byte will fail. It will come back and say there are no more bytes to read, and as a result, the read call returns a 0, and it terminates the loop, and when the loop terminates, the program exits. So do we have any questions about the C code? Because I'm going to base the rest of the program based on the C code. Are there any questions about the C code itself? Any questions about what read is returning, or the meaning of the integer returned by the read call? Questions? No questions? Okay, so if there are no questions, we'll put in the rest of the logic, because I do want to make this a little bit challenging. So we'll now detect, okay, do we see a lowercase with CH? And that can be done with a conditional statement. If CH is less than or equal to lowercase z, and CH is greater than or uppercase A, then we have just read a lowercase letter. Else if CH is less than or equal to uppercase Z, oops, and CH is greater than or equal to uppercase A, then we have an uppercase letter. So in each case, we have to do the kind of conversion from uppercase to lowercase, and the way to do this is to say CH plus equal to the difference between a uppercase A and a lowercase a. So now we can say it's just the difference, which is the ASCII code of lowercase a, whoops, the other way around, the ASCII code of uppercase A minus the ASCII code of lowercase a. So at this point, I don't even need I don't even need to look up the ASCII table, because I know that the alphabets or the letters are contiguous. Okay, so A to Z occupies exactly 26 contiguous spots in the ASCII table. And knowing that, I just need to offset the number by the right amount, and I'm all done. Is that making any sense? So if you just kind of think about the extreme cases, if CH is exactly lowercase a, then the calculation will first subtract lowercase a from lowercase a, which gives me a 0, right? 0 plus the ASCII code of uppercase A becomes the ASCII code of uppercase A. So the base conversion logic should work just fine. And I don't have to look up the table at all to find out what are the ASCII code of the characters. And this one is just the reverse. I'm changing from uppercase to lowercase. So we'll go ahead and test this program again and see if, I just lost my screen. That's okay, the program is still working. I just have to turn my head to see the screen here. And we'll go ahead and run this program again, and this time we'll say this is a test, and you can see how it changed all the uppercase to lowercase and lowercase to uppercase. The space is not affected. Digits and punctuations should not be affected either. And when I press Control D, the logic should still work and get me out of the program. All right. So do we have any questions about the code at this point? No questions? Yep, go ahead.
You hit Control D to exit?
Yeah, Control D on the keyboard, when your program is waiting for input and you press Control D on the keyboard, it signifies end of file. Because there's no other way to indicate it's the end of standard in, which is basically mapped to the keyboard. Now, when you test a program like this, you can also make a test file. So what you can also do is to say, I'm making a test file, and in the test file, you just give it, all the things that it's supposed to deal with, and you'll see if it works, right? So what you can also do in this case is to redirect, instead of typing something from the keyboard, you can redirect the input from a file so you can see the actual output. Or if you want to be even more systematic, you can also redirect the output into a log file if you want to. And now you can examine the log file at your leisure and spot what the program is doing. So that can also be done in in GDB. You can actually run a program in GDB with redirection of input and output, and I'll show you guys how to do that. All right, so we got the C version of this program up and running, so it's time to convert this into assembly. Or, well, the first thing we want to do is to flatten this first, okay? So to flatten this program, we'll start with the loop, and we'll do it one step at a time. When you do this, I strongly suggest that you save the original version, the way it is right now, before you make any modifications. Just in case the flattening part did not work, you know how to get back to the original program. But I'll just go ahead and do the changes in place here. So with a while loop like this, it becomes a little bit of it's not easy to translate directly because we have an assignment operation inside the loop. So what we're going to do here is to say this is the begin of a while loop. Unfortunately, we only have one while loop, so it's not there's no issue of which while loop we are talking about. And once we flatten this one, this will go away. And after the entire block, we have a unconditional goto going back to the beginning of the entire loop. We also need a end of the while loop, so we have while end as a label here so that we have a spot to land when it is time to stop. And then we go back into here and say, okay, what exactly are we doing here? The first thing we need to do is to actually call the read call, and then whatever the result of the read call is, we want to store it into result, and then we compare result to 1. If it is not 1, we get out of the loop. That's the logic. So what we do here is to do the assignment statement first, all by itself. So read equals, result equals to read 0 ampersand ch1, and then we'll compare result to 1. If it is not 1, which usually means 0, because it can either be 0 or 1 in this case, we go to the end of the while loop. And that basically that flattens the loop itself, okay? Are there any questions about this part, flattening the loop itself? Now, I'm not gonna, if I were to do this as a homework assignment, I'm gonna stop here and recompile the program just to be sure that it is working still the same way as before. So I'm going to use the same test case here. Now, this is a good time to test it using a different output, because then I can just compare the two files and see if they are the same. Is that making any sense? Okay, so we'll do it this way. And to compare files, I think there's a program called FC for file compare. Test.txt log versus test1.log. Nope, that's not FC. We can use diff for sure, so let's use diff. And diff does not indicate any differences, so the output of the two programs are exactly the same. The logic seems to be preserved. Okay. So now it's time to move on and flatten the other part, which are the conditional statements. Now this is a multi-branch conditional statement, which is actually a structured conditional statement. So the way to convert this is to get rid of this condition first, and basically turn it into saying, okay, if it is greater than Z or less than A, then move on to the else case. Okay, move on to the else if. So that means that if CH is greater than uppercase Z, then we want to go to the label called else if, and we'll define the label else if exactly here. If CH is less than lowercase a, that's also a good reason to skip around and go to else if. And if it is neither, okay, then we'll go ahead and, because we just got a lowercase character and it's time to process it. But after we process, we have to remember to put a unconditional goto to the end of the if. So we say end if here, and the end of the if is all the way down here. So we say end if as a label here. And you can see, the way I write this program is definitely not sequential. I'm not converting it from sequentially from the first line to the last. I deal with it in a structural way. I look at the structure of the program and say, okay, if I were to convert this structure and flatten this structure, what would I have to do? Okay, so this way, I kind of keep things slightly more organized, and it's not as difficult for me to remember what else I have to do. So now it's time to flatten this particular one, and we'll use the same logic. If CH is greater than uppercase Z, or CH is less than uppercase A, then it's time to skip around also, because we don't need any conversion in that case. So same logic. If CH is greater than uppercase Z, go to end if in this case. If CH is less than uppercase A, also go to end if. And if I end up here, that means CH is in fact one of the uppercase characters, and we can do the conversion in this case. Technically speaking, it is safe to say go to end if here, but since it's going to fall through to end if anyway, so this go to is not necessary. It doesn't hurt, but it's not necessary either. So are there any questions about the program at this point? All right. So let's go ahead and recompile this program. And we have test.txt as the input and test2.log as the output. Even though I could just overwrite test1.log, it's just a very tiny file, so I would much rather just keep it there and not mess around with it. And once again, we div test.log, which is the one from the original C program before any flattening, with test2.log. And once again, there are no differences. So at this time, we are ready to convert the program into assembly language. Okay. So we'll go ahead and cp cc.c to cc.s and edit this program. First thing first, change all the beginning of every single line to have 2 pounds to be safe. So this way, I have I comment out everything in this case. And then it's time to do the conversion. So for the conversion, there are a few ways to do it. So CH definitely needs a place, so it's going to be a dot byte, and the initial value doesn't really matter because we're going to override it by the read command anyway. And then we can switch back to dot text, the usual stuff, dot global underscore start as the start label, and then we can skip all the way to while begin. While begin, we can just keep it because it's the same syntax in C as in assembly language. Result gets read blah 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 means we have to move L $1 into EAX, because when EAX, nope, not 1 means exit, right? So we don't want a 1. Does anyone remember the number? I actually do remember, but I want to see if you guys actually pay attention. Really? 3. 3 for reading and 4 for writing, okay? So if you put a 3 into EAX, it means we are requesting the operating system to read from a file in quotes in this case, because the file is not specified by name, it is specified by file descriptor. So 0 goes into EBX. The address of the character that we'll be storing, the 1 byte that we are reading back, is $CH, that goes into ECX, and the last one is the number of bytes to read, which goes into EDX. Once all the registers are set up, it is time to ask the operating system to do it. So just like last time when we talked about how to raise the privilege level and request the operating system to do something at the same time, it's done by a software interrupt. A software interrupt is done by an int instruction, which has nothing to do with integer. In this case, it's interrupt. And $0x80 is the vector to that particular address. So that will basically cause the operating system to take control at this point and perform the actual read operation. When the read operation is all done and the int instruction comes back, then EAX will have the result. Okay, EAX has the quote-unquote return value, which is either 1, which means we just read 1 character, or 0, which means it's at the end of file. I could not read a single character anymore. Okay, so in this case, I'm not going to store result into its own memory space because it's just going to be in EAX. So at this point, I will compare EAX to 0. So CMPL Because we're dealing with 0 or 1, if you want to do a CMPB in this case, it will still work. But in general, it's not safe to compare byte when the return value is actually 32-bit. But in this case, yeah, it's going to work too. But let's do it right and not do it that way. So we compare 1 to EAX, which is actually my result. And if it is not equal to J and Z, go to the label called while end. And we skip to this part here. So this one is going to compare the character to the ASCII code of lowercase z. I can do it in several ways. So it depends on whether you want me to do it only using indirect and immediate operands, or do you also want me to kind of use direct operands. It's up to you. I mean, I can do it either way. If you want to do it the cisp way, then you want me to do it in a load immediate into register and then the indirect, compare indirect. If you want to do it in a kind of easier way with fewer instructions, then we can use the direct operand. So it all depends on whether you think the use of a direct operand is going to be confusing or not.
I said direct.
Sorry, go ahead.
Direct.
Use direct? Okay. So using the direct operand means it is easier because we can now just say compare byte. So in this case, compare byte is important. Okay, if you use the wrong width for comparing, it may never match. Okay, or it may match when it's not supposed to. So you have to use compare byte in this case. ASCII code of Z can be done like this. You don't have to look up the table because you can have any expression after the $, it will still be considered immediate. So that's fine. And then we are comparing with whatever byte in CH. So you can see that in this time, CH does not have a $sign in front of it because it's not an immediate operand. It is now a direct operand. Okay. So that's the compare, and the this part does not really matter because we're only dealing with the lower half of the 256 values. So whether it is signed or not, it really doesn't make any difference. In this case, we are looking for greater than, so it will be JG or JA. Both will work in this case. To else if, and then we handle this one, which is kind of the same thing, except we are comparing, but looking for comparing against a different character, and this time we are saying JB for J below, jump below, to else if. And then this part here, there are a few ways to do it. Since we're using direct operand already, might as well use it over here as well, which is really just an add byte. And the first operand is immediate, which is just uppercase A or the ASCII code of uppercase A minus the ASCII code of lowercase a. And then the second one is the immediate operand, which is CH. Not immediate, sorry, take it back. Direct operand of CH. And then we have an unconditional branch to end if, which is just a jump instruction to end if. So, are there any questions about the translation? Yep.
Up at the top, result equals something or other. Where is result? Is that EAX?
Result is in EAX,
Oh.
so I don't even bother to store it into memory location because we are using it right away, and
It's
there's no
gone.
need to know it. Yep.
Gotcha.
Yep.
Wouldn't you, this is a little confusing to me because I thought in order to do a subtraction you had to actually use like sub B or something like that. Whereas
subtraction?
we're just straight using the symbol for subtraction. For the
On which line?
For the subtraction, 33, for the subtraction of the ASCII.
But it's okay, on line 32, which is the C code, the right hand side of the plus equal operator is a constant. The displacement of uppercase and lowercase characters is always the same. So it is actually a constant, and I'm using it as a constant also on line 33.
Okay, so if it's a constant, we can use the symbols?
If it's a constant, you can make it an immediate operand.
Okay.
But it is an addition because it's a plus equal operation. It's not a minus equal, so it is an addition operation.
Okay, I was referring specifically to the uppercase A and the lowercase a and ASCII. character.
That part is a constant, and that's why we can just kind of put it into the just put it right to the right hand side of the dollar symbol, that will work too.
Okay.
Yeah. All right, so moving on. This stuff here is pretty much the same thing, Yep, go ahead.
So then, back to what he was saying, so I could put $10 minus 5?
Yeah.
Okay.
Absolutely. The dollar sign is really just a prefix to mean that whatever follows is going to be the value of an immediate operand.
Okay.
So you can say $L1, you can say $L1 minus 5, or you can have dollar and then a big huge expression like this.
Okay.
As long as every component of that expression can be resolved at link time, it will still work.
Okay.
Yep. So it cannot involve, let's say the use of registers or the content of memory. That would not work.
Yeah.
But the address of memory will still work.
Okay.
Yep. All right. So at this point, we move on to line 38. So pretty much boring stuff at this point because we have just done kind of like this, earlier. So I'm going to be a little bit lazy and do something that I'm not supposed to, which is copy and paste. Copy and paste is not nice because sometimes if I forget to change one of the labels, then it won't work, right? And I do that a lot too. So we put it here, and this one is comparing to A, and then we jump to and if over here, and then that is the same thing as this, except we're dealing with the opposite. Oh, we've done that already. Cool. I did not even know that I've done that already. And then we move on to, okay, I see what's going on. So paste here. Oh, we forgot the other one. Ooh. Uh-oh. Something is not right. Okay, so we have the original if statement. And then we have the else if here. The else if is here. So this does not belong here. That should be end if already. Let me double check.
You copied the too many lines.
Yeah.
This is why we shouldn't copy and paste.
Exactly. That's why we should not copy and paste. Very good. Okay, I think that's a duplicate. Because that should just be end if. There we go. I think that would be correct. All right. So after the end if, we have, okay, we have to define the label end if, which is easy. Just, get rid of all the comments, and then we have to write one single byte from CH to standard output. So this is almost the same thing. I'm tempted to copy and paste again because we have almost this code all the way up a little bit earlier. So what I'll do instead is to do everything from scratch so that I don't copy and paste. So the $1 goes into EBX, and then $CH to ECX, and then $1 to EDX. Don't forget the interrupt instruction. The software interrupt instruction is important because if you forget line 57, nothing happens. You set up all the registers and then you forget to file the form to the government. And obviously nothing gets done if you don't file the form. So you fill in the form, you file the form, you wait for an answer. But in this case, we don't really care whether the answer is yes or no because we just assume that byte is written to standard out. Then we have an unconditional branch to while begin. And we have the label while and here, just get rid of that. And then return 0 is just our usual way of exiting a program. And now we know what that means, right? Because putting a 1 into EAX means we are ready to exit the program. And then putting a 0 into EBX means that's the exit code of the program. And int $0x80 is requesting the operating system to let us out. Okay, I'm ready to go. All right, so let's go ahead and test this program and see if it works. Hi, Steve.
Just wanted to say hi.
Oh, hi.
I'll see you at your Christmas party.
Oh,
I'll
okay.
send you an email as well.
Okay, thanks.
You can forward that to us.
Hmm?
Said you can forward the email to us.
Oh yeah,
We'll be there.
it's a potluck.
Oh man.
Then people won't show up. It's like
No, I
potluck.
can't.
Okay, so we have CC, so we run CC, and I'm being really brave here, you know, and it seems to work. No, it's not working, is it? Okay, let's test it. Okay, so we'll make it make the output to test3.out, and then we use a div test.out, which is from the original C program before the flattening.
.log.
Oh, .log, and then test3.out, which is the last file, and they're definitely different. Now, even though it's not working, we can still learn a lot from the way it is not working. Okay, so instead of jumping back into the program and start staring at the code and scratching my head and go like, oh, okay, what went wrong? Let's analyze the output. Okay, I know it is wrong, but it's wrong with a certain pattern to it. Okay, so it is important to understand the pattern. You can see D, F, A, S, D, F, the uppercase ones, they're all done correctly. So lowercase to uppercase conversion is working just fine. The punctuations, exclamation point, at, pound, line feed, they're all working fine as well. So all the non-alphabet letters are working as well. What is not working is converting from uppercase AS to lowercase as. In the original C program, this is working. In the new program, that's not working. Now, but it's not working in a certain way, because if you look at ASDF and look at these letters here, the ASCII codes are all related. Okay, so that means that the conversion process from uppercase to lowercase is not working, right? But the program does recognize that there's a need to do the conversion. And I think I know why it's not working. It has to do with copying and pasting. Okay, because I'm using the same offset to do the conversion, which means it's not converting in the right direction, it's going in the opposite direction. So we go back to the program and we have to locate the code that deals with converting uppercase to lowercase. That's that's where the problem is. So converting from uppercase to lowercase is here. No, that's lowercase to uppercase. This is uppercase to lowercase. Okay, there we go. And the way I did it is wrong because I copied and pasted too much. So we should be going in the opposite direction. Compare line 47 to line 33. They're supposed to be opposite of each other. And I copy and paste too much and forgot to make the change when I copied and pasted. So another reason not to copy and paste, and also leave comments in the C code also. All right, so AS, LD, and just rerun it, test.txt as my input file, test3.log this time as the output file, do a diff of test.log to test3.log. Now they're the same, so the assembly code is now identical to the C code, as far as these test cases are concerned. Okay. Now for your program, you should also test it with more what we call boundary cases, like an empty file. Give it a file that has 0 bytes and see if it works. Because if you give it a 0-byte file, it should give you a 0-byte file as the output. Because there's nothing to read, right? If there's nothing to read, the output file should be empty as well. So are there any questions about this little exercise here? Yep, go ahead.
What did you use the register EDX for?
EDX is the count. It's basically the number of bytes that you're requesting to read or requesting to write. So in this case, we are only requesting to read 1 byte because we are processing 1 byte at a time. Yep.
So you're using EDX, ECX, and EDX, like after the interrupt, would all the values get erased and then you use them again?
I would not count on the registers maintaining their values after the call. So if you need to reserve a value in a register, you probably want to reserve some memory locations and copy the register into memory first, and then copy it back from memory. We haven't really talked about the push and pop instructions, so I cannot tell you guys to use those instructions to save and restore the registers. So the other way is basically just to allocate some space in memory and then use move L to move the content of the register into memory and then the other way around.
But like would the value of the read would be erased from the registers?
It can overwrite, the software interrupt instruction can potentially overwrite the values of the registers. So I would not count on the registers being preserved. Any other questions? Now, if there are no other questions, I will just kind of pop the program back up a little bit, and you know, it's gone. This won't take long. I just want to explain the approach of doing things like this. In other words, I just want to explain this piece of code here using the registers to indicate what needs to be done and the parameters of doing it, and then have a software interrupt instruction to actually get the operating system to do something about it. This is actually universal. I actually looked it up. It's exactly the same way using Linux on an ARM processor. Now, obviously, the instructions are different. Okay, you know, they don't have the same instructions as the i386, but the approach is still the same. You set up the registers, and then you have a software interrupt instruction, and it triggers the operating system to do something about it. So this is a pretty much universal way for a protected mode program to ask the operating system to do something. That really is the most important part of learning this stuff here. It's not the exact instructions, but the approach of doing things. All right. Any other questions?
So for our project, it's to convert from base 10 to hexadecimal and backwards?
I don't think it is inverting back. It's just reading a hexadecimal number and then store the value into a memory location. That's basically what you need to do.
Okay. That involves multiplication, right?
Nope.
No?
Nope. The C code actually does not have a multiplication either.
It just has a lot of adds.
Yes, because if you double 4 times, it's the same thing as multiply by 16.
Yeah.
Yep.
So we can't try using a multiplication because
The multiply instruction is tricky on its own. So if you want to learn how to do it, I can give you guys a little slide of how to do it. But it's, in a way, it's not worth the trouble because the multiply instruction has a side effect that most people do not remember. And getting bitten by that one is not worth the time because it's like, my program is not working. It's only because people forget that the instruction modifies 2 registers instead of 1. So we can talk about it, but the code as it is right now should work as well. Right. Any other questions? Yep.
So you said hex to 10, right?
Yeah.
Okay, good.
No, not to 10, just to the internal representation, which is base 2.
Base 2, okay.
So when the program is done, the variable will have the actual value that is represented as base 16 when it comes from the standard input.
So we put in the hex, so.
From standard in will be a hexadecimal number, base 16 number. Your program will read it, and when it's done reading it, one of the variables will have the actual value of that base 16 number.
Okay.
Yep. All right. Any other questions? So that should be all the pieces that you need for your homework assignment. And last time we talked about how to read already. So what is missing is just the write operation that we just covered today. So that means we are ready to move on to, let's see, are we in this class now? Nope. All right. So let's move on to talk about some of the practice questions for next Tuesday's exam. And I only got time to put some of these here, but there are some more questions from earlier, so we can go back to those if we have time. Oh, never mind. Go back a little bit. So for those of you who are feeling kind of adventurous because the homework assignment is too simple as it is, you can read how to multiply and divide and use multiplication. get it working first, okay, and then you say, okay, this is really cumbersome because we're using 4 add instructions to implement multiply by 16. Save that program, turn it in first, and then try to use multiplication. If you can get multiplication to work, great, turn it in again. If not, you can just say, okay, it's not working. All right, so practice exam questions. This is only a small sample of the questions. I'll give you more on Thursday. All right, so let's focus on these 2 instructions. Question number 1. What is the status of each flag? And those are the 4 ones that we have to deal with. Carry, 0, overflow, and sign. Okay, this is supposed to be S and not V. This is supposed to sign and overflow after the following instruction execute. So we first move a immediate 23 into AL, and then we subtract 34 from AL. So the question is, what should the flags be? Okay, you are allowed to use a scientific calculator, or I will bring in a whole big bag of Dollar Tree calculators that you can also borrow from me. But I don't think you will actually need that for stuff like that. Okay, so what do you think? 23 in decimal minus 34 in decimal. Should the carry flag be set? Yes, it should be set because a borrow situation happens. The carry flag is the borrow flag. What about the Z flag? The Z flag should be cleared because the result is definitely non-zero. What about the sign flag? Sign flag is set because the result will have the most significant bit set. What about the overflow flag? It should be cleared. Okay? The overflow flag should be cleared. Now, the sure way to do this is to carry out the calculation in binary. Oops, wrong tool. Okay, so let's do it in binary. If you want to do this in binary, 23 is 16 plus 4 plus 2 plus 1. Okay, so that will give me 0x, let's see, 0, 0, oops, not 0x. This is in binary. Okay, so it's 0b for binary, 0, 0, 0, 1. That 1 is the 16. And then we have 0 for the 8, and then 1, 1, 1 for 4, 2, and 1. So that should be the binary representation of 23. And then the next one is 34. 34 is an easy one because it's just 32 plus 2. So that will be 0b binary, 0, 0, 1. That's the 1 for the 32. And then 0, 0, 1, 0 for the 2. So that turns out to be a pretty easy number to convert. 0, 0, 0, 1, 0, 1, 1, 1 minus 0, 0, 1, 0, 0, 0, 1, 0. And we'll do it the same way as I usually do in class, separating the 2 subtraction into 2 different rows, and each row represents the result of 1 half subtractor. So that so this concept maps directly back into the half subtracting concept. 1 minus 0 is a 1. 1 minus 0 is a 1 with no borrow. So put a 0 here. 1 minus 1 is 0. 0 minus 0 is 0. And neither contributes a borrow, so the borrow is a 0. 1 minus 0 is a 1. Oops. Right there. 1 minus 0 is a 1. And neither contributes a borrow, so this borrow is also a 0. 0 minus 0 is a 0. 0 minus 0 is a 0. 1 minus, neither one contributes a borrow, so this borrow is also a 0. 1 minus 0 is a 1. 1 minus 0 is a 1. We don't have a borrow from either one. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. Oops. 0 minus 1 is a 1 with an extra borrow. So when you look at this result here, the 0 flag is cleared because this is non-zero. The sign flag is a 1 because the most significant bit of the result is a 1. The borrow flag, which is also the carry flag, is a 1. So now the question is, how about the overflow flag? The overflow flag is basically saying, does it make any sense that if I subtract a non-negative number from a non-negative number and the result turns out to be negative, does it make sense? Is it possible? Yeah, sure. I mean, 1 minus 2 is negative, so it makes sense. So if the sign of the result makes sense, then the overflow flag is cleared. So that's how we get to the result of this particular question. And the next one is kind of the same thing, except it's an addition instead of a subtraction. And it also kind of tests to see whether you understand how the registers are structured. Yes?
So the overflow flag cleared that last one, the question one?
Yeah, the B flag should be the sign flag. I just made a mistake. Instead of using S, I use a B.
Because we're subtracting 34 from 23.
Correct.
That was a positive number, right?
The result, well, it depends on the sign flag of the result compared to the sign flags of the numbers that you're subtracting. So as long as the sign of the result still makes sense, while interpreted signed, then the overflow flag is cleared. So let's go to question number 2. Question number 2 is a little bit tricky because the first instruction is dealing with a 32-bit register, and then the second instruction only deals with an 8-bit register, which is a component of the 32-bit register. And also the value that I specify here is also a little bit tricky. What is 256 in binary? It's 1 followed by 8 zeros. Okay? So that means the least significant byte of EAX is 0. So the second instruction only affects the least significant 8 bits because it's an add byte instruction. So that means we're just adding 4 to 0. Adding 4 to 0 will not give you a carry. Okay, because 0 plus 4 is 4, there's no carry. The Z flag is cleared because 4 is non-zero. The sign flag is cleared because 4, the representation of 4, does not need a 1 in the most significant bit of an 8-bit number. And then the overflow flag is also cleared because 0 plus 4 is 4, or adding a non-negative number to a non-negative number, ending up with a non-negative number, makes sense. So the overflow flag is also cleared. Question number 3. It's kind of like the same kind of question, except this one is a little bit opposite. What is a value? Just give me a value instead of a range of values, which would make it more fun, but a value would do in this case. That can take the place of the question mark. So fill in the blank so that the overflow flag is set after the following instructions. So, give me a value that you put here so that the overflow flag will set after the add byte instruction.
255.
255 won't do it.
No?
It won't do it. This is an addition, so we are looking, what are we looking for? Okay, let's think about it. We're trying to add a non-negative number to something, and then the result will have the sign being kind of wacky, doesn't make any sense, right?
27.
So when you're adding non-negative numbers to something else, in what situation would the sign not make any sense? What about the sign of the question mark? Okay, should this be a positive non-negative number or a negative number? Now think about it. If you add a non-negative number to a negative number, the result can be positive or negative, right? So in either case, it will still be making sense, and the overflow flag will be clear. I want the overflow flag to set to become a 1, which means I cannot have a negative number for the question mark. It has to be a positive number. Is that okay so far? Now, if it has to be a positive number, then we are looking for the situation where I'm adding a non-negative number to a non-negative number, but ending up with a negative number. Okay? So we have to cross that most significant bit boundary to make this happen. In other words, I can think about the extreme cases. 127. 127 is the last positive value when you look at an 8-bit number and interpret it unsigned. So if you add 127 to 37, yeah, we have that number unsigned, but signed it is not a positive number anymore, and as a result, it does not make any sense. So in this case, if you want an easy answer, 127 is the easy one, because it is the highest possible positive number with a signed number in 8 bits. Is that making any sense? The way to approach this question. Okay. What about the smallest number that will still make it overflow? What is 128 minus 37? That would be the number. Because that's the smallest positive number. When you add 37 to it, will basically turn on the sign bit. Is that okay? 128 minus 37 is 91. So if you plug 91 into the question mark, 91 plus 37 is 128 exactly, and 128 overflows because the sign bit becomes 1 at that point. But it's the smallest number that can overflow it. Okay, because if you go for 90, then 90 plus 37 is 127, and 127 is 0, and then followed by 7 ones. So the sign bit is not flipped, and if the sign bit is not flipped, the sign still makes sense, and the overflow flag.
Can we just use a negative number?
Huh?
Can we just use a negative number?
No, negative numbers won't work, because if you add any positive number to a negative number, the result can be either positive or negative, so neither one will set the overflow flag. So a negative number will never trigger the overflow flag to set in this case. All right, moving on. Question number 4 is kind of the reverse of your homework assignment. So instead of making a register a particular value, we're just going to move forward. So we start with these definitions here, and in each step, I want you to tell me the values of the registers that it affects. Okay, so that's basically what the question is. So let's go ahead and approach this question and see how we can answer this question without the use of GDB. So that's the other thing. Even though we'll be taking the exam in room 128, it's going to be a paper test. So we're not going to use GDB or any of the tools. So it'll be a paper test. It is open book, open notes. Okay. If you feel there's anything that you can print or handwrite that will be useful in the exam, prepare and bring it in. Okay. It can be textbooks, can be my own notes, can be screenshots from the videos. Okay, so it can be anything that is either printed or handwritten, prior to the test. It will still be okay. All right, so in this case, what we want to do is to first understand how memory is going to be laid out first, because just like our homework assignments, that really is going to play a big part of answering this question. So what we want to do is to say, okay, the memory is going to be laid out like this. So we have 2, 3, 5, 6, F3, because those are 3 individual bytes. And then with the dot word, we have to be careful because of little endian representation. So F3 is the one that has a lower memory address. 5, 6 is the one that has a higher one for the first dot word. And then the second one of the dot word will have 5, 6 as the least significant byte, which has a lower address, and then F3 being the one with a higher address because it's the more significant byte. And then we have L1 taking up 4 bytes. We don't know exactly the content of those 4, so we just say L1, 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 and L1. It takes up 4 bytes. And then the next 4 bytes will be taken up by L1 minus 4, or the 4 bytes that are used to represent L1 minus 4. So let me change the screen here a little bit so we can actually see that. So we have L1 minus 4, L1 minus 4, and L1 minus 4. And then after that, we have the single dot int after that. That one is also a little bit tricky because I did not specify all the leading zeros. So without the specification of all the leading zeros, you need to fill that in. The least significant byte is F3. The second least significant byte is 5, 6. And then we have a 0, 3, and a 0, 0, because it has to take up 4 bytes. So you have to use zeros to fill up the entire thing. So that's basically how memory is going to be laid out. Let me see if I can change the editor in a way that will take up less space vertically, but it will take up more space horizontally. There we go. All right, so this is how memory is going to be laid out. And where exactly is L1? Okay, let's take a look at the original code first, and then we'll figure out where L1 is supposed to go. Okay, there we go. So which byte should have L1? Remember, L1 is a label of a single byte. Okay, so which byte should have L1?
That
Ah, very good. That one. So that being
first L1 minus 4.
right here. Okay, this is where the bookmark is. L1 is the address of the least significant byte of the dot end of the value of L1 minus 4. Is that part okay? Now remember, the address is only of a single byte. So L1 is the address of the least significant byte of the dot end L1 minus 4. Okay, so knowing this, now it's time to actually trace the code and find out what it is going to do. Oh. I thought I had vimium installed, but the keystrokes are not working. There we go. So now we have the rest of the program, and we'll just try to figure out what this program is going to do. The first instruction is to move L1 minus 4 using a $, which means it is immediate, to EAX. So the question now is, what is that going to move into EAX? Or what will be the value of EAX after this instruction? It will just be L1 minus 4, right? It's a move immediate operand, which means whatever I specify with the first operand is the value that will be put into the register. So let's go ahead and do that. I'm thinking about how to do this. I know exactly what. I'll turn this into an editor, so this way I can actually put in the answer in place. There we go. And pop the other one back up like that. Okay. Put the cursor here. There we go. All right. So at this point, EAX should have the value of exactly L1 minus 4, because that's what the instruction calls for. The next instruction is going to subtract 9 from EAX. So as a result, EAX will have the value of L1 minus 13, because L1 minus 4 minus 9 is L1 minus 13. And then we actually do a dereference. I think I might have made a mistake here, so we'll see. L1 minus 4, we can only have up to 7. So I'm going to change the question a little bit here. So I'm going to doctor this a little bit so that it works. Okay. All right. So what would be the value of EBX after this move L instruction? Oops. Let me go back to the other one so you can see. There we go. What do you think? It's going to be, okay, let's count the bytes. This is L1, L1 minus 1, L1 minus 2, L1 minus 3, L1 minus 4. Oh, the original code actually may work. Okay. What was it again before?
9.
9. But we changed that to -4, and this would be minus 8. That will work. That will work. Okay. So let's count. This is L1 minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. This is L1 minus 8. So L1 minus 8 is the starting point of the move L instruction. But since it's a move L instruction, it's going to move how many bytes? 4 bytes, starting with the F3. So F3 is going to be the least significant byte. This is going to be the second least significant byte, and so on. So the actual number that is being moved is F3, 56, 56, F3. So at this point, EBX has a value of 0x F3, 56, 56, F3. And then we subtract 1 from EAX. In this part, I don't need the editor, because EAX, if we subtract 1 from L1 minus 8, what do we get? L1 minus 9. Yep, exactly. L1 minus 9 is here. So when we switch back to the content of memory, this is L1 minus 8 already. This is L1 minus 9. And where are we copying L1 minus 9 to? We are moving byte indirect EAX to BH. Okay? So out of the entire EBX, which part is BH? It's not the least significant byte. The least significant byte is BL. Okay? It's the least significant byte, which is the one that has 5, 6 right now. So I can highlight which one we are talking about. So the second least significant byte is this byte here. So 5, 6 is the one that is going to be affected. So that means, as a result, EBX as an entire register is going to be 0x F3, 5, 6. F3 again, because that's the one 8-bit chunk that is overwritten by this instruction. And the rest of the register remains exactly the same, because when you move something into BH, the entire register EBX, except for those 8 bits, remain exactly the same. So that's basically the answer, because you only have to trace it up to stop here, and the stop here label is right next to it. Are there any questions about this particular question? It's kind of the reverse of your homework assignment, where in your homework assignment, I give you a target value in a particular register, and you have to figure out how to work it out so you end up with that value in a register. In this case, it's the opposite. I give you the program to begin with, and you have to trace the program step by step to get to the answer. Yep.
Take a look at the text editor again.
Absolutely. There we go. Actually, what I can do is that won't work. It won't work because I didn't use a fixed size font in the editor, because otherwise it's not gonna line up. Question?
No, I wasn't sure that the F3
Oh,
was the
okay.
same. So I wasn't sure what was the next one.
Question?
Pretty sure you said that we get to some point and then we get like an error or something, like from the test. Would that be partially credit? Or like with the overall?
With something like this, it's kind of be evaluated sequentially, so you get partial credit up to that point, up to where up to where your answer deviates from the actual correct answer. Any other questions? So questions like this is kind of nasty in a way, because you have to track down a lot of things, but at the same time you can get partial credit. For anything that is easy, like the first few questions, they are simple, but there won't be any partial credit, because there will be partial credit if you get like 3 of the 4 flags correct, and the remaining one that is wrong, you still get partial credit for that. Any questions about any one of these questions? On Thursday, we'll go over some more questions, which is in the form of I give you some code, and you have to tell me what's wrong with it and how to fix it. So I'll give you the C code, I give you the flattened assembly code that implements the C code, and you have to tell me, which part is incorrect and how to fix it. So that's kind of spotting problems, which we do with your homework assignments and also in class. Yep.
Programs?
To actually have you to write programs during the test, no, because those things are way too hard to grade. And you won't like it either because, okay, there are several ways to have exams, with a class like this. In the past, when we have enough room in the lab so that everybody can have a computer, I have tried a practical exam where I just give you the C code and your job is to implement it in assembly. Okay, so I have tried this. I have tried that before, and it didn't work out very well. The reason why it did not work out well is because it's almost impossible to give partial credit. I would say 80 or 90% of the submission did not work completely, or did not compile, did not assemble. But they got most of the stuff done, like the control structure is kind of there, but not entirely there. But the program does not work in the end. So how am I gonna grade it, right? How do I assign points when the program is sort of working, but sort of not working? But with this type of problem, like I give you the C code, I give you the assembly code that is not implemented correctly, then I can check, okay, with all the things that went wrong with this code, how many did you catch? I can give you partial credit. You don't have to catch every single one to get, some points. You can get some of them right, and you still get partial credit. So that's why I don't want to ask, practical questions, because I tried it before and it just did not work out. And people panic about it because by the time the exam ends and the program is still not working or not even assembling, people start to panic, and that's just not something that is nice. Whereas, as opposed to, okay, spot all the problems and fix them. So if you spot the majority of it, you know that you're going to get some credit for it, right? Even though if you don't catch every single one, you'll still get some points. Okay. Any other questions about the test, the exam?
How many questions is there?
I haven't decided yet because it depends on the complexity of the questions, like how difficult each question is. But there will definitely be at least one more type, which is to fix a program that I write. Anything else? Yep.
Is it going to take the whole lab period?
Yes, it will take the entire lab period. So it will go from 10:30 to 11:50. Yep.
Is what we're seeing representative of accurate representation, or?
I stopped answering that question a long time ago.
Right. That's not good.
Because what I say, yes, this is representative. People come back to me and say, this is nothing like the actual test. And some people say, yeah, well, that's pretty close to the actual test. And then some people say, it is confusingly similar to the practical test. It is not fair. Because I just say, oh, in the original test I use a move B instruction. In the actual test I use a move L instruction. It's a minor change that can change a lot of things down the line, right?
But if we understand this, we're good.
That would be about the scope.
Okay.
Yes.
Okay, good.
Mm-hmm. Okay. Any other questions?
When are more questions going to be added to this?
I'm going to add it as soon as possible. So on Thursday, we'll definitely go through all of the practice questions. And the homework assignment, for believe it or not, is going to help you prepare for the test as well. Okay, because the whole thing about flattening a structured program, file input, file output, that stuff is going to be in the test too. So while you're writing your program for the homework assignment, you are actually studying at the same time. There's nothing that will require memorization because it's open book, open notes. Okay, so anything that you think you might forget, just write it down on a piece of paper, bring it with you. Okay? So it's not about memorization, it's about how well you can apply the concept that you have learned in this class. If you have been doing the homework assignment, it's actually spending the time to let the concept soak in and stuff like that. It should be okay. I mean, I'm not going to ask too many questions where time becomes a real factor. Any other questions before we move on to the next topic? Because we got 5 minutes left, but I think we really kind of have to press on, just because there are quite a few more concepts to talk about in this class. No questions for now? All right. Well, Well, if you do have questions, bring those questions, to the class on Thursday, okay? Because we do have one more session before the exam, so that would be a good time to answer the questions. All right, so let me save and go back to the course. And we are now moving on to topic 7. Now, topic 7 is really an important topic because this is the pivot point to go from control structure, which is just conditional statements, loops, and so on and so forth, to subroutines and how to use local variables and how to use parameters in a way that is consistent with the C compiler. So when we are done talking about this stuff here, you will be able to write assembly subroutines that can interface with C subroutines in both directions. So you can call an assembly subroutine from C and vice versa, okay? In assembly, you can call a C subroutine. You can call printf, you can call scanf, and so on and so forth. Okay? So that means this is a really, really important concept. And it starts with the concept of a stack, okay? So the stack is basically a concept based on last in, first out, okay? Are there any questions about what is last in, first out as opposed to first in, first out? Give me an example of first in, first out.
Queue.
A queue, a line, when you go to Costco, when you go to Walmart, when you line up to pay for something, that's first in, first out. Or at least it is supposed to be first in, first out. Until someone cuts in and, someone with 6 children, one child in each line, and then the parent go oh, I think that one's going faster. Go over there. And then they move to the other line that seems to be going even faster, right? Yeah, I used to be one of those children, so I know. I hope my mom is not listening to this. So that's first in, first out. And also buffering is first in, first out. Okay, when you watch Netflix or YouTube, your player will do a first in, first out buffering. Okay, the frame that arrives to your computer first will be the frame that is played first. Okay, and it's very useful. FIFO is really, really useful. But LIFO is just as useful in computer science, even though in real life, most of the time it is a hindrance. Okay, it's not something that we would like to do, but it's just that certain things are structured that way, and that becomes last in, first out. Give me an example of last in, first out. Well, I mean, you can read the example up there, but you can also come up with something else.
Hanoi Towers. Hanoi Towers.
Hanoi of towers. Tower of Hanoi. Yep. So Tower of Hanoi is a puzzle problem, but it is also a last in, first out thing, because the last disk that you put onto a stack is the first one that you remove. Yep.
No, never mind. It wasn't.
Okay. But I use U-Haul here as an example, because when you load up a U-Haul truck, so let's say you're really well prepared, you have the map and everything ready, except when you load up the truck, you kind of put down the map first, thinking that this is important. I make sure that it is in the truck, and then you load up the whole truck, and then what do?
You look at the map, you're like, oh crap.
Exactly, your map is the hardest one to get to because it's all the way in the inside. The last thing that you push on the truck, which is usually a bicycle or something, is the first thing that falls out when you open the tailgate, right? So that's last in, first out, classic last in, first out, and sometimes it doesn't work out the way that you want it. A refrigerator is also last in, first out. By its very design, a refrigerator is last in, first out, because when you buy new stuff, let's say you just went to Costco with your mom, and then you got a lot of stuff, right? So you load it up in a refrigerator. How many people will restructure everything in the fridge first? Take out everything that has been sitting in the fridge for a few days, take it all out, put all the new stuff all the way back to the fridge, and then put all the stuff that only has a few more days to last, to the front of the fridge. You do that. Okay, you do that. Okay, but most people don't, right? So what happens to the back of the refrigerator? It becomes a fungi botanical garden, right? I mean, you have all kinds of fungi and various types of color going on, and until you cannot stand it, right? Then you buy even more stuff to cover it up. It's like, oh, I don't see that stuff anymore. That's not a problem. Or I'm just making cheese. That's not milk, that's cheese. I'm just making cheese. Just wait another 3 months and we got good cheese going. Okay, but that's last in, first out too, but it's only by the nature of the storage, it is last in, first out, okay? All right, so last in, first out is the key concept of a stack, okay? Now with a stack, in terms of assembly language implementation, the key concept to implementing a stack is a stack pointer, okay? So we want to look at the stack pointer and say, okay, but what is a stack pointer? The stack pointer is officially ESP, registered ESP is the stack pointer. It is a special purpose register, which means even though you can use ESP in add, move, and all the other instructions, just like EAX, EBX, ECX, and EDX, there are specific instructions that only work with ESP. It is also an implied operand in those instructions. It is not spelled out, it's just implicit. The value of ESP, okay, the register itself, is basically the address of the next byte to remove. Or you can also interpret it as the last byte that you put onto the stack. Okay? Are there any questions? Now, I know I'm running out of time, but I do want to at least get this part done so that we have at least this concept done. The stack grows down to lower memory addresses. So let's take a look at memory here. So let's just say that this is a chunk of memory, and this is high address, this is low address. Okay? And let's just say that the stack pointer is at this point currently. If you want to store, let's say, a 32-bit integer onto the stack, okay? So let's say we want to store A, B, C, D, 1, 2, 3, 4 as a hexadecimal number onto the stack. The way you do it is you store this number onto the stack, and the least significant byte will still use little endian. Okay, so when you use little endian, then 3, 4 is the least significant byte. It should be at the lowest point, and AB is the most significant byte. So when you store that number onto the stack, then you have AB, CD, 1, 2, and then the 3, 4. The stack pointer is supposed to point to the very last byte that you store on the stack. So how should I move the stack pointer? Towards
lower memory.
the last byte, right? So the ESP or the stack pointer is not going to be moved to 3, 4 because that really is the last byte that we store on the stack. And that's called pushing something on the stack. When you store something on the stack, it is called pushing. To remove something from the stack, it is called popping. Okay, so you can remove items from the stack. We are running out of time today, so I will continue with this discussion and also programs to illustrate these concepts on Thursday. Okay, but it really helps if you can read ahead of me a little bit. And I'll be at the lab today at 10:30. Okay, so if you want to do your homework assignments or ask questions, regarding the homework assignment, this will be a good time to do it.